Welcome to this laboratory session. Today we are going to see the determination of thickness of a thin object using air wedge method. Here the apparatus required is two optically plane glass plates, a sodium vapor lamp, a thin wire or the thin material whose thickness we desire to find out, and a traveling microscope. Here is the experimental setup. As you can see here, this is the sodium vapor lamp, which is sending out a monochromatic light of wavelength 5893 Armstrong units. And here it is the traveling microscope apparatus, which is used to find the distance between it is used to find the very near distance. And this is a 45-degree glass plate. And we have two optically plane glass plates here. And here the thin object kept is a cellophane paper whose thickness is to be determined. Before going on to see how to do this experiment, let me give you a little theoretical background on this air wedge experiment. So actually what happens here is we have the light from the sodium vapor lamp will be falling on this 45-degree glass plate. This 45-degree glass plate will be used to render a parallel beam of light into this air wedge arrangement. And on the air wedge arrangement, what happens here is the light that is falling on the top glass plate will be reflected back, and half of the light will get refracted into this air medium and gets reflected from the bottom glass plate. Actually, the air wedge arrangement is the bottom glass plate. This is our top glass plate. The light that is falling on the top glass plate, partially the light falling on the top glass plate is reflected as ray 1, and the remaining part of the light getting transmitted through this air medium inside the two glass plates gets reflected from the bottom glass plate. And there will be certainly a path difference between these two rays, that is ray 1 and ray 2. Ray 1 is getting reflected from the top glass plate, and ray 2, after getting transmitted through this air wedge, gets reflected from the bottom glass plate. And certainly there is a path difference. Due to that path difference, we will be having constructive interference or destructive interference depending upon the path difference between this ray 1 and ray 2. And what is an air wedge? Air wedge is nothing but, see, this is the bottom glass plate, this is the top optically plane glass plate. At one end between these two glass plates, we are keeping the object whose thickness is to be determined, and it is tied at this end, and this end is also tied. Right? Now if you see the air gap between the bottom and top glass plate, it is in the form of a wedge. Right? This shape we call it as wedge shape. So the air gap in between the two glass plates takes the form of a wedge, and since the wedge is filled with air, this is called air wedge. Right? So the light coming out of the sodium vapor lamp is rendered into a parallel beam of light by that 45-degree glass plate, and the light which is coming towards this air wedge setup, a part of the light gets reflected from the top glass plate, and the second part of the light which gets transmitted into this air wedge gets reflected from the bottom glass plate. And due to the path difference between these two waves, that is ray 1 and ray 2, there is interference that takes place. This path difference between these two rays decides whether the interference is constructive or destructive. So we have here the path difference between the rays 1 and 2 is given by 2d plus lambda by 2. How come this 2d plus lambda by 2? Let d be the distance from this point to this point. So the first ray gets reflected from this point itself, from the top glass plate, and the second ray traverses a forward distance of d, gets reflected back, again it traverses a distance of d. Right? So the total distance traveled by this ray 2 inside this air wedge is equal to 2d, and due to the reflection there will be a phase difference of exactly 180 degrees. That will give you a path difference of lambda by 2. So the path difference between this ray 1, which is getting reflected from the top glass plate, and the ray 2, which is getting reflected from the bottom glass plate, will be equal to 2d. This is the distance traveled by the ray 2 in the air wedge, plus this path difference lambda by 2 is due to the phase difference of 180 degree that happens due to reflection at the bottom glass plate. Right? So the path difference between ray 1 and ray 2 is equal to 2d plus lambda by 2. If this path difference is equal to integral multiple of lambda, you will be getting a bright fringe, and if this path difference is equal to half integral multiple of wavelength, then you will be getting a dark fringe. Right? Say for example, let us consider 2 points here, that is A and B. At A, let us consider this triangle ABC, right? So let's consider this triangle ABC, where this angle is taken as alpha, so this angle will also be equal to this alpha, and now tan alpha is equal to opposite side by adjacent side. Since this is 90 degree, this AB will represent hypotenuse, and this is the angle alpha, this is our opposite side, BC is the opposite side, and this is our adjacent side AC. So tan alpha in the triangle ABC, tan alpha is equal to BC by AC. BC is opposite side and AC is adjacent side. So we have tan alpha is equal to BC by AC. This BC is taken as lambda by 2. How come it is equal to lambda by 2? Let me come on to this diagram. See here. If the path difference is integral multiple of lambda, you will be getting a bright fringe. And if the path difference is half integral multiple of lambda, you will be getting a dark fringe. Now we need to find what is the distance in the path difference to get the thickness of this dark band or bright band. Right? So let us take this point as lambda and this point as lambda by 2. That this lambda and lambda by 2 represents the difference in path. Say for example, if this is at this point, if the light produces a bright fringe, the path difference will be equal to integral multiple of lambda. And let us consider another point B, where the path difference should be half integral multiple of wavelength. If it is half integral multiple of wavelength, it will give you a dark fringe, right? The next consecutive dark fringe. So if I am able to find what is the distance between these two, that will give you fringe width. Fringe width is nothing but it is the distance between either two consecutive bright bands or two consecutive dark bands. If I want to find the width of this dark fringe, I need to find the distance between two consecutive bright fringes, right? So this path difference is integral multiple of lambda, and this path difference is half integral multiple of lambda. Say for example, if this path difference is equal to lambda, this path difference is equal to lambda plus lambda by 2, right? This extra path difference should be lambda by 2, so that this represents a dark fringe, right? So the value of BC can be equated to lambda by 2. Hence we can write here tan alpha equal to BC by AC. BC is equal to lambda by 2. How come it is lambda by 2? Because this is a bright fringe, this is a dark fringe, the next dark fringe. So the path difference for a bright fringe should be an integral multiple of lambda, that is, let us take it as lambda, and this should be half integral multiple of wavelength. So we can take this path length as equal to lambda, that is B dash C can be taken as equal to lambda because this distance is lambda. So let us take this distance also equal to lambda. So to make this light to be giving a dark fringe, this distance BC should be equal to half integral value of wavelength. That is, BC should be equal to lambda by 2, so that the light reflected at this point gives you a dark fringe. So we have, instead of BC, we have lambda by 2 divided by AC represents beta. What is this beta? This AC is equal to this A dash B dash. The value, the distance between this A dash and B dash can be taken as beta, which represents the fringe width. That is width of either a dark fringe or a bright fringe. So we'll take it as beta. So lambda by 2 by beta, that will give you lambda by 2 beta. And similarly, when you consider the triangle O, P dash and P, we can write tan alpha equal to, again opposite side by adjacent side. So tan alpha is equal to P dash by OP dash, that is tan alpha is equal to P dash by OP dash. Let T is the object, thickness of the object. This is the object which is kept in between the two glass plates at one end. So let T be the thickness of this object. This thickness we need to find out using this experiment. So we have PP dash is T and OP dash is L. So this becomes tan alpha is equal to PP dash by OP dash. That becomes T by L. So we can equate these two things because this represents tan alpha, this equation also represents tan alpha. So comparing these two equations, we can write T by L is equal to lambda by 2 beta, or the thickness of the object that is kept in between the two glass plates. T is equal to L lambda by 2 beta. That is the equation that is used here. See, we have T is equal to L lambda by 2 beta. This is the equation that is used to find the thickness of the given object. Here L represents length of the air wedge, lambda represents wavelength of the light used, and beta represents fringe width, which is nothing but the width of either a dark fringe or a bright fringe, which can be calculated by calculating the distance between two consecutive bright fringes or two consecutive dark fringes. And the value of this beta will be calculating using a traveling microscope. So let us move on to how to do the experiment. Let us see how to do the experiment. So this is our traveling microscope. It is provided with a horizontal scale as well as a vertical scale, but for this experiment we are going to use only the horizontal scale. Let me show you the reading on this scale. So this scale you call it as a main scale, and this one you call it as a vernier scale. As you can see here, the vernier scale consists of 50 divisions. Each division represents 1, right? So each of this division represents 1. So we have got totally 50 divisions on the vernier, and on the main scale, as you can see, the divisions between 1 centimeter, this main scale is calibrated in centimeter. 1 centimeter is divided into 20 divisions, right? So what is the value of 1 division? If 20 divisions, if 1 centimeter is equal to 20 divisions, then say for example, let 20 divisions is equal to 1 centimeter. So 1 division is equal to 1 by 20 centimeter, right? Let me write it here. See, on the main scale, 20 division represents 1 centimeter, right? So 1 division, the value of 1 division is equal to 1 by 20 centimeter. That is equal to 0.05 centimeter, right? Let me show you the main scale. This is the structure of the main scale. If this value is equal to 2 centimeter, this value is equal to 3 centimeter, and in between this 2 and 3 we have got totally 20 divisions, right? Each of these divisions represent 0.05 centimeter. So if it is equal to 2, this will be equal to 2.05. The other division will be, you have to add another 0.05 over here. So 2.05 plus 0.5, it will give you 2.10, right? So by logic also, see here, if this is 2, this is 3, the center reading should be 2.5, and between this 2 and 2.5, we have 4 divisions. This is 2.1, 2.2, 2.3 and 2.4, and between this 2 and 2.1, we have one more division. So on the halfway between 2 and 2.1, we have 2.05. So 20 division constitutes 1 centimeter, and therefore 1 main scale division is equal to 1 by 20 centimeter. That is equal to 0.05 centimeter, right? So let me show you the scale again. So you can see the scale here. Between 3 and 4, we have got 20 divisions. We have got 20 divisions. This represents 3.5. This represents 3.1. And between 3 and 3.1, we have 3.05. Right? How will you take reading? MSR, that is main scale reading, is nothing but it is the division on the main scale which is completely crossed by this vernier 0. Right? So the reading on the main scale which is completely crossed by this vernier 0 will give you main scale reading, and the division on the vernier scale which completely coincides with any one division of the main scale gives you vernier scale coincidence. Right? Let me tell you once again, main scale reading is the division on the main scale which is completely crossed by this vernier 0. Right? And vernier scale coincidence is that reading, that division on the vernier scale that is in complete coincidence with any one of the division of the main scale. That you call it as vernier scale coincidence. Here the main scale reading is, this reading is 2, this is 2.1, 2.2, 2.3, 2.4 and 2.5. Here the vernier 0 has crossed 2.5 of main scale, and hence you can write main scale reading is equal to 2.50. And if it crosses the small division, if this vernier 0, if it had crossed this small division after 2.5, you might have written it as 2.55. Now the main scale reading is 2.50, and if you check the divisions on the vernier scale, not all divisions will be coinciding with the divisions on the main scale, but only one division on this vernier scale, might be 2 or 3 divisions may get coincided with any division of the main scale. You need to check the vernier scale from 0. You have to check the division, the first division that is in complete coincidence with any division of the main scale. That gives you vernier scale coincidence. You will be given with a lens, an optical lens, to check the vernier scale coincidence. Let us move on to the fringes. So as we discussed in the theory, when the light from the monochromatic lamp falls on this 45-degree glass plate, it is rendered parallelly into this air wedge arrangement. You have got a thin paper here. We need to find the thickness of this thin paper. That thin paper is kept in between the two optically plane glass plates at one end, and both the ends of the glass plates were tied tightly with a rubber band. Right now, we need to adjust this traveling microscope. We have to focus the traveling microscope so as to see the fringes in the eyepiece. Right. So this represents eyepiece, and this represents the objective of your traveling microscope. We do have 3 arrangements. We can adjust the height of this microscope by using this screw. Right. This is the screw. This is the screw that is used to change the vertical height of the microscope. This is the main screw used to change the horizontal distance of the traveling microscope. See, if we can loosen the screw, this traveling microscope can be slided easily on this main scale. Right? If this main screw is tightened, we can use the tangential screw to make fine adjustments. If I move this tangential screw clockwise, you can see the vernier scale, we need to keep this main screw in a tight position. Then we can use the tangential screw. You can see here. Let me show you the movement of this tangential. See, now the vernier scale is sliding over the main scale. As you can see here, it is moving towards the vernier scale, is moving towards my left. Right. So when I move this tangential screw, when I rotate this tangential screw in a clockwise direction, you can see the movement of vernier towards my right. So this tangential screw is used to have fine adjustments, and this main screw is used for coarse adjustment. Right? We can make this traveling microscope to move horizontally as well as vertically. We do have 2 main screws and 2 tangential screws. This is the tangential screw for vertical movement, and this is the tangential screw for horizontal movement. And apart from that, the tilt of the eyepiece can be adjusted using this screw. This screw can be used to adjust the tilt of this microscope, and this is the focusing screw which adjusts the distance between the objective lens and eyepiece lens. If we keep this microscope at a proper height, and if we adjust the tilt screw as well as this focusing screw, we will be getting fringes. Right? Let me show you the fringes over the microscope. Let us try to observe the fringes in the microscope. I hope it is visible. This is how the image looks on the eyepiece. Now keep your vertical crosswire on one dark fringe, measure MSR and VSE. Move your vertical crosswire to n plus 5th fringe, n plus 10, n plus 15, etc. Observe MSR and VSE. Let us see how to do calculations. LC represents least count, which can be found from the formula value of one main scale division divided by number of vernier scale divisions. As we had seen already, value of one main scale division is equal to 0.05 centimeter, and there are 50 divisions on the vernier scale. So LC is equal to 0.001 centimeter. So how will you calculate CR for the first value? MSR plus VSE into LC. MSR is 3.50. So 3.50 plus VSE is 16. into LC is 0.001, that is equal to 3.50 plus 0.016, that is equal to 3.516. You write the value of CR over here. Similarly, you can find CR for all the rest of the values. Then you need to find distance, we need to write CR over here, 3.516, 3.669, 3.811, and you can fill this column for up to the last reading. Then how do you fill this column? This represents the distance between 10 bands. See, this is the distance of nth band and this is the distance of n plus 10th band. You need to find what is the distance between nth band and n plus 10th band. How will you do? This is the distance of nth band. This is the distance of n plus 10th band. So if you find the difference between these two values of CR, you will be getting the distance between 10 fringes. Right? So I need to calculate 3.811 minus 3.516. That will be my first value. And what is the second value? I need to calculate the difference between n plus 5 and 15. I can take 10 and 20, 15 and 25, 20 and 30, 25 and 35, 30 and 40. So if I'm able to find the differences between the values of CR over here, I'll be able to fill this tabular column. If I add all these values and take mean, I'll be getting what is the value for mean 10 beta, right? Mean 10 beta is equal to dash point dash dash dash. Make sure that you are writing 3 digits after the decimal point, because here LC is equal to 0.001. So make sure that you are having 3 digits after the decimal point. Now after taking the mean 10 beta, we need to calculate what is the value for mean beta. So mean 10 beta is equal to this much and mean beta is equal to this value divided by 10, or we can simply take this 10 to the numerator and simply convert this 10 power minus 2 to 10 power minus 3. The same value into 10 power minus 3 meter will give you mean beta. And how will you calculate L? See, our formula is T is equal to L lambda by 2 beta. We have calculated the fringe width beta from table number 1. 2 is an integer. Lambda represents wavelength of the monochromatic light that is used. Here we have used sodium vapor lamp whose wavelength is equal to 5893 Armstrong unit. 1 Armstrong unit is equal to 10 power minus 10 meter. So we have values for beta as well as lambda. Now we need to calculate the value for L. What is L? L represents length of the air wedge. See here, this length, that is, you have to keep your vertical cross wire at one end of the glass plate which is farther away from the object, right? You need to keep your vertical cross wire at this end. Let it be A. You have to take value in this tabular column. This is tabular column number 2. Now edge of contact, this is the edge of the glass plate which is farther away from the specimen. So the main scale reading is taken as 4.10, 1 year scale coincidence is taken as 26, and we have calculated the correct reading. And to calculate this length L, we have taken one reading at this edge of contact, and the second reading should be taken at this point, right, at the starting point of the specimen. So you need to use this main screw. You can loosen this main screw and make your traveling microscope to slide through your traveling through the main scale, and make sure that your vertical cross wire sees the starting point of your specimen, right? So this is the second place where you need to measure the MSR, where you need to observe the MSR and VSE. So you keep the vertical cross wire on the specimen, take the value of MSR, observe the value of VSE, calculate the value of CR. So we have taken one reading at this point and have taken another reading at this point. If you find the difference between these two values, you will be getting the value of L, that is length of air wedge. So this is one value which is at specimen. This is the other value at the edge of contact of the glass plates, that is farther away from the specimen. If you take difference between these two values, you will be getting the length of the air wedge, that is 4.269 into 10 power minus 2 meter. Now we have the values for beta, this lambda as well as this L. Now if you substitute the value for L, lambda and beta, you can calculate the value of the thickness of the specimen which is kept in between the two plain glass plates, right? You can see here there is a cellophane tape that is placed between the two glass plates here. If you are able to find the value of fringe width using this two glass plates with specimen, you will be able to calculate what is the thickness of the specimen. T is equal to L lambda by 2 beta, and after finding the thickness, you can write it here over the result. This is how you can determine the thickness of a thin specimen using air wedge method. Thank you.